G'day, in this video we're going to be looking into diffraction and Young's double slit experiment, which helped to verify the work of Huygens and his wave model. In this video we're looking at dot point 7.2.1 and 2. We're still looking at the classical wave model of light and the predictions that can be made using it, some of the phenomena that can be explained by the wave model. And here we're going to be analysing the diffraction of light, particularly through a double slit apparatus, which is going to be used to replicate Young's double slit experiment and show this particular quantitative relationship here that can be observed when conducting the experiment. We're also going to be looking at some other different slits that cause diffraction, particularly diffraction gratings. So we're going to qualitatively and quantitatively investigate the interaction of light when it diffracts after passing through a set of double slits. And then we're going to be looking at the similarities that exist in diffraction patterns for a single slit scenario as well as our diffraction gratings. So, Young's double slit experiment. Essentially, this guy here, Thomas Young, sent some light passing through two double slits. And when he did so, he was able to measure quite an interesting pattern out on the other end. When he looked at the light that came up on the viewing screen, he saw areas that were quite bright that clearly came from the original light source, but in between areas where there was complete darkness. There were essentially maxima and minima. And this can be explained by the destructive and constructive interference that occurred when waves from both sources of the slits converged on a single point. If they met out of phase, then destructive interference was experienced and there was a dark spot. And if they met in phase, then there was constructive interference that was observed and the brightest spots were seen. First and foremost, what was noticed was that there was a lot of light that converged into the center, and this was the brightest spot. But there were then these other antinodes which occurred on either side where there was brightness observed too. And there was a distinct pattern in their distances. This was observed and helped to support this wave model because the waves, instead of just traveling directly straight through the slits as Newton would have predicted, instead traveled out radially in all directions once they passed the barrier. So what that meant was that once these wave fronts passed the barrier, there were sections where the light from both slits were able to interact, even though they weren't directly aligned with the light that came out originally. This again supports the idea of the wave model of light. What I'm going to be doing in the coming slides is helping to unpack essentially this style of diagram here that you would see that shows a double slit experiment and demonstrate to you some of the quantitative relationships that exist as a consequence. So in your data sheet, you're going to see this equation that d sine theta is equal to m lambda. Now there's a lot going on here with a lot of different measurements, so I want to try and unpack that for you as best as we can. Essentially, if you've got your waves coming in, right, with a wavelength lambda, which we can see in our formula here, that light is only going to be able to pass out from the two slits. But again, they will come out radially, and therefore there will be areas of constructive interference, as have been marked out with the antinodes, and then you would expect to see nodes where there is destructive interference directly between each point of light. We also have these m values, which are always integer values. They have to be a whole number, and essentially they mark how many bright spots are we away from this central spot that's there in the middle that would be in line with the center point of our gap here, D. If we were to measure from this central point, this y value would measure out the distance from the center to our next point of light, one of our antinodes. We have an L value here that measures the distance between the slits and the viewing screen. And then, as I said before too, we also have D, which is the width of the two slits as well. And that matches up in our formula too. So where does this formula come from? Essentially, if I were to draw this diagram here significantly more zoomed in, what we would start to draw out here are two lines which are in essence parallel to each other. And the reason why we're going to run with this assumption that both rays that are traveling towards the m equals 1 spot over here parallel in the first place is because D, the gap between the two slits, is extremely small. Certainly, compared to the length that the light will be traveling, it is significantly small. When we start doing this practically, you'll see what I mean. The gap between the slits really small. The distance that the light has to travel before it gets to the viewing screen significantly larger. And so because of that, even though in this diagram it's quite clear that the lines aren't parallel, and no matter what, right, these lines are technically never parallel, they may as well be because the angles of both of the lines are so similar. So when we run with that assumption, we can start doing a lot of geometry, which makes our analysis make sense and straightforward and get us to this formula here. Yes, the formula is based on assumptions, but again, those assumptions and error that comes from the assumptions are negligible. So we've got our two lines here. They're both pointing towards m equals 1, the first antinode, which isn't in the center. What I can do is draw a line that starts on the top ray, ends at the bottom ray, and this line that we draw is perpendicular to both of the rays. Essentially, it's a line that cuts our parallel lines, but is also perpendicular to both of them as well. This here makes a triangle, and it's a right-angled triangle. I've drawn it in here a little bit bigger. The line that runs directly up and down is the distance between the ends of the two slits. Again, we've got a right-angled triangle here, and we've got theta, the angle between our D line and this perpendicular line. What you'll note here is there's a little bit of a gap, and this gap we can assume to be exactly lambda, the wavelength of whatever the ray is. In this case, I've drawn it to be. Now, the reason why this has to be lambda is because if we're going towards m equals 1, both of them, and there's constructive interference occurring here, then both of the waves have to be in phase with each other. If they're in phase, that means peaks match with peaks, troughs match with troughs. And if that's the case, because both lines, while being, again, assumed parallel, because they have to travel different distances, we can't just say that we've got two sets of parallel lines that start at the same spot and end at the same spot and are the same length. Geometrically, both lines have slightly different distances. But to end up in phase here at the end, essentially, let's say theoretically, and this is just a number, there's 1,000 oscillations between here and the end. Well, here there must be 1,001 oscillations to get from the beginning to the end. And that extra oscillation, the 1,001st oscillation, is this little gap here. Because from this point onwards, we're all going towards our meeting point at m equals 1, and they're the same distance. And essentially both of these lines here would be the same distance from there to there. Again, we're running on assumptions. The geometry doesn't exactly work out, but again, because this angle here, theta, is so small, the gap here is so small, the length here is so big, you can run with those assumptions, and the errors that you get with running those geometric assumptions just become negligible and don't actually matter. So what that means is I can use a trig function to say that sine theta is equal to lambda on D, or that D times sine theta is equal to lambda, which is pretty similar to the actual formula that we have in our data sheet. But it's also got this M feature in here as well. And that's because these lines, these rays, will point to different antinodes that are a certain number of antinodes away from the center. So we could have m equals 1, 2, 3, 4, 5, etc. If I were to draw up the same scenario again, but instead have my rays traveling towards m equals 2, so that would they go to here in this diagram at the top, then that's going to change up the geometry a little bit here, essentially because the angle here is going to be a little bit larger. This distance here has to be larger as well. And because, again, both waves have to be in phase by the time that we get to m equals 2, this distance is going to be equivalent to 2 lambda, 2 wavelengths. If we were to use our 1,000 waves analogy, if there are 1,000 oscillations between here and m equals 2 point that's over here, there must be then 1,002 oscillations for this line, and the extra 2 are here in this little gap. And so that means that sine theta is equal to 2 lambda divided by d, and that d sine theta is equal to 2 lambda. And we should start to see a little bit of a pattern here. If m equals 1 in this scenario, then there's a 1 and a lambda. And if m equals 2 in this scenario, then there's a 2 multiplied by a lambda, m lambda. If we were looking at the rays traveling to any of the other m values, any of the other antinodes that if we were to extend our viewing screen would end up being dotted along here, then again, the same thing, d sine theta would be equal to whatever the m value is multiplied by a lambda. And in each of these scenarios, this theta value would be getting progressively larger and larger to account for that. So that's where our formula comes from here. However, a lot of the time, we don't actually work with just this formula as it's shown here. A lot of the time, we will have a missing theta value and one of the other variables being potentially missing as well. For example, when we do this experiment in class, we're going to know d, the distance between the slits that we pass our light through, but we are not going to know theta, and it's going to be nigh impossible to measure. We'll be able to figure out what m is because we'll just be able to count out the dots that we see on a viewing screen, but we also won't know lambda. So I'm going to give you a laser to shoot through these double slits, and we're going to be able to take measurements and all sorts of stuff, but you're not going to be able to tell me what theta is because we don't know what lambda is. And conversely, you're not going to be able to tell me what lambda is because we don't know what theta is. And so there's another mathematical assumption that, again, we could make, which geometrically and mathematically is going to show there being inconsistencies and inaccuracies. But again, because of the scenario where d is really small and the gap between the slits and the viewing screen are really, really big, it is going to mean that this assumption or the errors that occur from this assumption will be negligible. So drawing out the big picture here, we've essentially got 3 lines. We've got our 2 rays, which again, we're assuming to be parallel, but I've also drawn another imaginary line that goes from the center of the slits, so right in between the 2 edges of the slits, this midpoint here, to m equals 1 point as well. And again, because of how our geometry works, even though these angles aren't going to be identical, we're going to assume that they're all parallel. So if that's the case, then we can draw out this angle here that we're going to call theta prime. And it makes essentially a right angled triangle with the horizontal distance between the slits and the viewing screen, which we call L. We've got theta prime here in the middle, and that's essentially the angle between this line and the line that goes to m equals 1. So this point here is this point here, which means that the distance between m equals 1 and m equals 0, the central point of light, is going to be equal to y, this distance here. So we will know d, that is going to be given to us on the actual slit itself. We can measure L and we can measure y, and these are very easy measurements to make. So how is this geometry all going to work out? How do these assumptions come into place? Well, essentially, when L is large compared to D, then theta is going to be very small and close to 0, whether it's this theta here or this theta here. Essentially, these are pretty much the same as each other. And this is based on the assumption that these 2 lines would be parallel to each other. There's a geometric proof, assuming that they're both parallel to each other. I'm not going to bog you down with the details, but we're going to run with that assumption again because of the relative differences in the distances D and L. So if theta is small, it's close to 0, then what we can say is that sine theta is going to be pretty much the same as tan theta prime, which is this angle here. And tan theta prime is equal to opposite divided by adjacent, y divided by L. Therefore, even if we don't know what this theta value is, assuming that it's small, which it will be, we can therefore run with the assumption that d sine theta could also be written as d times y divided by L instead. And what that means is we remove the theta variable, something that we can't very easily measure for, and instead estimate what that would be by inserting y on L into our equation instead. And from there, we can measure d, we can measure y, we can measure L, we can know the m value, and therefore calculate for lambda. There are some other diffraction scenarios that we can look at as well. Maybe you've got a large single slit instead. What will generally happen is that there will be some degree of diffraction around the edges, but most light will end up congregating around the center. But you will still get some sort of splitting a pattern, again, like we saw in the double slit experiment. And the general explanation for how and why that happens is that both of these edges will act as a slit, some sort of point source for waves where you will end up with diffraction on either side, meaning that you will end up with areas where there is constructive interference and areas where there is destructive interference. And so again, while most light will pull itself in the center, you will get these antinodes with a small intensity of light. We can also work with diffraction gratings, and these are essentially a series of slits that are really close to each other and stacked on top of each other, and there's just opening after opening after opening. It would look a little something like this, right? So they all have different densities. They're marked on the slide themselves that has it, but yeah, there's a bunch of different slits that the light can pass through. Essentially, when you've got light coming from all of these different slits and combining, there are going to be very, very finite and specific regions where that light actually congregates, comes together, and constructively interferes, which means that you're going to get these really small, thin, bright spots as compared to your double slit, where the bright spots are a little bit larger and wider, and their brightness sort of disperses around the edges. As a general principle, a higher density of slits will decrease the width of these maxima even further. But again, this is something that we'll unpack a little bit more in class 2. Thank you very much. In the next video, we're going to be looking at the final concept for the wave model. We're going to be looking at how the wave model is able to explain how and why light polarizes, and look a little deeper into a law that applies polarization, which is Malice's law. But until then, have a good one.